All right, so we've gone through and seen most of the basic effects of phonons in a toy model of a one-dimensional chain. Initially, we did a monatomic chain where there was just one atom per unit cell, and then we did a marginally more complicated case of two atoms per unit cell. And what we saw there was that we got these new type of phonon vibrations called optical phonons. That were qualitatively different and had quantitatively different frequencies of vibration than what we saw in the monatomic chain. Now, that's a very simplified case, but it has a lot of the makings of reality, but it's missing some stuff. So what I'd like to do now is go through and actually do the real full case of phonons in 3 dimensions. We wouldn't have wanted to start here because, as you'll see, there's a lot more notation to keep track of and a lot more mundane things. But if you actually want to go on and do more complicated science or more realistic science than what we've done so far, you really need to do this in 3 dimensions. So let me just remind you of some basic things we found in 1 dimension, and let's see how we can extend those into 3 dimension. So in 1D, we sought displacements that looked like essentially wave-like solutions. So we were looking for things like, let me write it as the displacement of an atom in the nth unit cell was U0 e to the I, and I'm going to write this in a weird way this time, Q times L times A, minus omega t. Now, actually, when we went to go solve this, I used a slightly different notation for the monatomic chain. I had been calling this, we had called this K for wave vector. You'll see that I need to change the notation here. You'll see why in a second. And the other thing is I had previously called this N. I'm going to use L here, and you'll see why in a second. So let me just make sure that I explicitly say this. So Q in this case is the wave vector. So this is actually a very common notation for phonons. So people like to actually distinguish the wave vector for phonons from the wave vector for electrons. So for electrons, they always use K as the wave vector. And for phonons, oftentimes you'll have mixed, like, we haven't solved any problems like this so far, but oftentimes people who are interested in transport have electrons running around at the same time as phonons. And so in order to distinguish the wave vectors of those two things from one another, people will generally use Q as the wave vector for phonons and K as the wave vector for electrons. Let's see, and the other thing is that I'm going to use this. So L was essentially a way for us to index of the unit cell. So previously we had like, we had called it N, but I'm sorry, I wrote L here, but what I meant was that previously I had called this N. So previously N ran from 0, 1, 2, 3, 4, 5, 6, 7 all the way up to infinity. And in fact, it doesn't have to start from 0. In principle, you could march it backwards too. But anyway, so previously we sought solutions in this form, wave-like solutions, in this wave-like form. What I'd like to do is use that for inspiration to seek a 3-dimensional solution that would be more general. So here's what we're going to do. So in 3D, we'll seek something very similar looking. It's just that I have a lot more things to keep track of. So in addition to the fact that the displacements in 3 dimensions don't necessarily have to be along the direction of like a particular direction. They can be in any of 3 dimensions. So in fact, what I'm going to do is I'm going to adopt the notation. Let's see, I didn't say this, but the notation I'm going to use here is by U and Cardona. You can, if you're interested in looking up where some of this stuff comes from, this is part of their textbook called the physics of semiconductors, I believe, or the fundamentals of semiconductors is Ewan Cardona's textbook. So anyway, so in 3 dimensions, what we're going to do is we're going to seek displacements u, except for there could be multiple directions of displacement. So let me call it u sub I, where here is I is the direction of displacement. So that's, x, y, or z in three dimensions. And then I'm also going to keep track. So previously I was keeping track of the unit cell number up here. Now in 3 dimensions it's a little bit more complicated, because in addition to being able to move unit cells in this dimension, the unit cells actually go up and into the page as well. So I need to be a little bit more careful about this. So I'm going to assign an index which has a vector L. So there's more than one index, so I can index it in both the x, y, and z direction, or it's not even necessarily x, y, and z, it's just along the lattice vectors that exist. And the other thing is that, what I wrote up here would be fine for a monatomic chain, but when we were solving for the diatomic chain, we found out that we needed to seek more than one of these type of solutions within each unit cell. So like when we did the diatomic chain, we had written u and v, and we simultaneously solved for the displacements of u and v. The way I'm going to denote that here is I'm just going to solve for 2 different u's. I'm going to index them by k. This is the reason why I didn't use k over here. If I'm following Ewan Cardona's notation, k is the kth atom of the unit cell. So for example, like silicon is in the diamond structure. Silicon is in the primitive lattice is an FCC lattice, but there are 2 atoms per unit cell. So if I was solving for silicon, I would have to solve for not just one of these things u, but I would have to solve for one associated with the first atom and one associated with the second atom. So in that case, there'd be 2 atoms per unit cell, and then this thing L is is a unit cell, or is an index for the unit cell. And so in particular, I did this really poorly. I wrote in an area here where I actually need to be able to write. Let me write out the rest of this, and then I'll fill in the value of u again. So I never actually finished the equation. I just started writing the notation here. So what I'm going to say is that is given by a wave-like solution that has to do with the values that occur in the first unit cell times e to the I q, where the wave vector is now literally a vector dotted with a translation vector that is an integer multiple of the lattice vector minus omega t. So a little bit more about this. So L here is, an index for unit cell. And in particular, what I mean by that is that the translation vector, so the lattice vector, or the integer multiple of the lattice vector, is defined as L sub 1 times the first lattice vector plus L sub 2 times the second lattice vector associated with the unit cell plus L sub 3 times the third lattice vector associated with the unit cell. And of course, like L1, L2, and L3 basically can take on, that whatever that tuple is can take on, any of those can take on values that are like 0, 1, 2, 3, all the way up to infinity, and maybe even count backwards depending on how you're doing the accounting for how you're numbering the unit cells. But the basic idea is that, if I compare these two things, so this is ultimately what we're going to do. Let's see if I compare these two things that are boxed, basically they look very similar. So the idea is that I'm going to write the displacement in any arbitrary unit cell based on what's going on in the first unit cell times a wave-like, phase factor. And that's the basic idea. So everything is completely analogous. It's just that there's a lot more notation to keep track of because you're doing things in 3 dimensions. So you've got 3 directions, but then also the unit cell indexing has to be done in 3 directions, and you can have more than one atom per unit cell. So keeping track of these indices is a lot more of a pain. But in principle, the basic idea for how you seek wave-like solutions is exactly the same. Okay, so this is the form of the solution that we'll seek. Let's talk about, what equation of motion that we're actually going to solve. So we spent a little bit of time developing the equations of motion for the diatomic chain and the monatomic chain. In the 3-dimensional case, in some ways it's a little bit easier, but in other ways there's a lot more notation to keep track of. So let me do a separate board about how to handle that, and then we'll plug in and see what that infers about how we actually go about solving for the phonon dispersion relationships, and see what kind of interesting things come up related to the eigenvectors that'll come out of that. All right, let me cut this off, and I'll